All right, this is problem 381, where we have a cantilevered beam with another offset beam, and a little stub there, and at the very end is 175 pounds applied in the positive y direction, and 100 pounds applied in the positive z direction. Okay, so part A of this problem asks for the precise location of the critical stress element. Where would it crack? And these forces are going to create moments, and the maximum moment is going to be here at this point A, somewhere along that beam. Now, because we only care about that point there, we don't really care what happens here. I'm going to redraw this a little simpler model. That's a bad one. A little simpler model, just consisting of two pieces with those applied at the end here. So here we have our beam, and there's our other beam. We have our 175 pounds, and then our 100 pounds kind of applied at that point here. This is still 5 inches, and then this is representing the 6 inches and the 2 inches for a total of 8 inches. There's our ground. All right. So what we can do is we can move these forces to this point and then eventually to this point, and then apply, and then also add the moment that would create around that point to create an equivalent force system. I'm going to move that 175 there, and then I need to add the moment that it creates by being in this direction with that offset. So that is a moment in the positive x direction for a total of 175 times 5. Let's add that moment there. 175 pounds times 5 inches, which is 875 inch-pounds. Okay. I got my force, got the moment it created. Now I can move this 100 pounds there as well. But it doesn't actually create a moment around this point because that point is still in line with the direction of that force. Okay. Now I'm going to do the same thing again, move 175 here, and then I need to add the moment that it creates around this point, which is going to be in the positive z direction. Okay, so there's my moment created. Here's 175. I need to take 175 times 8, which is 1,400 inch-pounds. In the positive z direction. Okay? Don't forget to move that moment there as well. That's still 875 inch-pounds. And then finally I'm going to move that 100 pounds in the positive z direction, move that there. 100 pounds. But then I also need to add the moment that it creates around this point, which it's going to be 100 pounds times 8 inches for 800 pounds. And the direction, if I use our right-hand rule, it's going to curve around, and that goes down in the negative y direction. 800 inch-pounds. So now, around this point A, we have 1, 2 forces, and 1, 2, 3 moments that were created by these two original forces. So I'm going to draw that cross-section here. Okay, so this is A. Here's my y-axis. There's my z-axis. So kind of looking straight down the shaft here. The x-axis, positive x-axis, comes straight out of the paper towards us. Okay, and I'm going to add my forces on there. So, and moments. So at first I have 175 pounds. I have that 100 pounds. And then my 3 moments. In this direction I have, put it down here, positive 1,400 inch-pounds. Going in the negative y direction, we have that 800 pounds, 800 inch-pounds. And then the one that's coming going in the positive x direction, that's coming straight out of the page towards us. So I'm going to show that as a counterclockwise moment, 875 inch-pounds. Okay? All acting right at that moment. So what I can do In order to find the critical stress element, where is that going to be located on this circle? Because we know it's going to be on this circle. We're going to take these two moments and find the resultant moment. That's going to go somewhere in this direction. I'm going to call that MB because it's the bending moment there. And MB is just going to combine these two vectors, square root of squaring them. So we have 800 squared plus 1400 squared, and take the square root of that for a total of 12.5 inch-pounds. Okay. Now to find the direction there, I'm going to label this as my theta. We'll get to that in just a second for that. So theta is equal to the inverse tangent of, in this case, the 1400 over the 800. Which comes out to 60.3 degrees. Okay. So the reason that I took this as my theta is because this moment, it's a bending moment. It's going to cause its greatest amount of stress perpendicular to its line of action. Okay, so there's the line of action. Perpendicular to that is here. Right? And thinking about the way it's going to compress this portion, and it's going to add tension right here. And this is the location of the critical stress element, because most materials will break under tension before they'll break under compression. And this is located because this is our theta. That's the exact same as this theta. Okay, so we know for part A that the critical element is located 60.3 degrees clockwise from the negative z axis, right? Negative z axis is here, going clockwise. There is our critical element location. Okay. While I'm here, I'm also going to find the resultant force that's acting on this. Somewhere up here, just call that Fr. Okay, and Fr is the resultant force that's 175 pounds at the 100 pounds. So we'll square those. We'll square root that for a total of 201.56 pounds. And if I wanted to find the angle, because of the way this is set up, it'd be the angle from here to here would be the inverse tangent of 175 over 100, which has the exact same ratio as this, and we get that same 60.3. So it's that shows us that this resultant force is acting completely normal to our stress element here. That'll come in later. All right, part B asks us to draw that stress element and then find all the stresses acting on it. So I will start off by drawing my little element there. I'm going to call this the x-axis. So that is, we're looking at this from this direction. Okay, so this x-axis, which is coming straight out of the board, this element would be perfectly vertical here. Okay, and then this perpendicular direction is actually here. All right, and actually we don't need to worry about the stresses there because of the way we set this up. We took the resultant moment of these for our bending moment, so perpendicular to that line of action, there aren't going to be any stresses that we're going to care about. Okay. So to find the stress in the x direction, the formula for that is the stress caused by bending plus the stress caused in that axial direction, which is x. Formulas for that, the bending stress is 32 times the bending moment divided by pi d cubed, okay? Plus the axial stress is your normal stress, which is going to be the forces in that x direction divided by the area, which, if you remember from our original problem, There are no forces in the x direction, so this goes to 0. I'm plugging in the numbers. We have 32 times our bending moment of 16.12.5 inch-pounds divided by pi times our diameter. Now, in the original problem, I didn't write it down, our diameter is 1 inch just at that point. So we have 1 inch cubed. Okay? Running those numbers together, we get 16,000. We have inch-pounds divided by inches cubed, which comes down to psi, pounds per square inches squared. 16,000. I'm going to write that as 16.42 ksi. Okay? So our stress there is 16.42 ksi. Okay? Again, we don't have to worry about the stress in this perpendicular direction, but we do need to think about the shear stress, and that's going to act here. I'm going to hold off on the direction for just a second. So the shear stress is equal to 16 times the torque around that divided by pi d cubed. Again, negative on that. We'll get to the negative in a second. Which is equal to negative 16 times. Now the torque is this 875. That's twisting our rod here, our shaft. So our 875, and that's in the positive direction. So that's a positive 875 inch-pounds divided by pi times our 1 inch diameter cubed. Okay. So when I run that together, I get a negative 4.46 ksi. Okay? So let's work with that negative there. This is on the side, the positive x, which is the same side I found this this stress from, the bending stress. This negative means that this is going to go in the negative turning direction. So if this was positive, it would come out of the board, it would twist it this way, but since we have a negative answer, we know it's going to go this way. Okay? And then our other ones follow suit. That goes there, and that goes there. So on our element, we're going to put that the shear stress is equal to 4.46 ksi, and the negative is taken care of by our arrow going in that direction. Right, and that's part B. For part C, it wants us to find the principal stresses there. The formula for that, stresses 1 and 2, is equal to the stress that we found there. I'll call that stress x, plus the stress in that perpendicular direction, divided by 2, plus or minus the square root of that same stress, that's perpendicular divided by 2, quantity squared, plus our shear stress squared. Plugging in the numbers, we found that to be 16.42 ksi. Our perpendicular stress we said was 0, divided by 2, plus or minus the square root of 16.42 divided by 2 squared, plus our negative 4.46 squared. So we're going to get two stresses, stress 1 and stress 2, coming from either the plus or minus here. So stress 1, when we run that together, we get 17.55 ksi. And stress 2, from subtracting it, we get negative 1.13 ksi, and the negative corresponds to it being a compressive stress versus a tensile stress. The third stress we're going to work on is the maximum shear stress. And that is just this square root portion here. So I have the square root of 16.42 divided by 2, quantity squared, plus my negative 4.46 squared. which comes out to 9.34 KSI. And that's those are the principal stresses.